Okay, in this video I'm going to get you started on 12.1 and 12.2. So let's look at 12.1 and let's look at an example from A so that you can have practice doing the other one. So the first one says, what is the log base 5 of 3? And the problem with this, of course, is you don't have a log base 5 in your calculator. So you use the rule that the log base anything of 3 of a number is the ln of the number. So ln of 3, and you say, oops, but it's not an ln, it's a log base 5, so all you gotta do is divide by the natural log of 5, and then you plug those in your calculator and you get the answer. Now you don't have to use natural log, you could use a log base 10, which in a calculator is just written log, and it would still work, and I don't know why I'm using parentheses here and not before, but oh well. So same difference, you just take the log of the number and you go, oops, it's a 5, not a 10 or an e, and then you have to divide by that. Okay, so I think the other ones in part A you should be able to get. Okay, then let's look at an example from B. They have like, okay, log base 3 of x is equal to e, and we want to figure out what x is. Since we have a log base 3, then we want to raise this to a base of 3, so we put 3 in the bottom here, raise that 3 to that power. Now we got to do the same thing to the other side, 3 to the e power. 3 log 3 cancel. That's the whole point. They're inverse functions. So over here we're just left with x, and x then is equal to 3 to the e power, which you plug into your calculator and you get the answer. Now we can always guess roughly what it's going to be, which is always a good idea. E is 2.71828, a little less than 3. 3 to the third is 3 times 3, 9 times 3 is 27. E is a little bit less than 3, so the answer will be maybe 23 or something. So anyway, you can figure that out. Okay, that's an example from part B. And let's do an example from part C. One of the ones they give you is 3y is equal to 10 to the x. So what power do we raise x2 to get 3y here? Now we're going to have a y in our answer, but that's okay. But we want to get x is equal to something with y's in it. Okay, we have 10 to the x power. The way you get rid of exponents like that is you take the log of both sides. Since it's a 10, which is nice, we can take the log base 10 of both sides. So on this side we have the log base 10 of 3y. On the other side we have the log base 10, and again if it's a 10 you don't need to write the 10, it's assumed, of 10 to the x. Log and 10 cancel, this side is just x, and over here we have the log of 3y. So we just have that the log of 3y is equal to x. And that's good enough. Okay, so that's examples of how to do 12.1. Now let's look at 12.2. So 12.2 says that as light penetrates water, its intensity decreases, which makes sense. Light doesn't get through water very well, so this is a true thing. They say it decreases 15% every 3 meters it goes down. Okay, by the way, that does not mean 5% every 1 meter. There's a little bit of a difference there, but it's 15% every 3 meters. So then they say, okay, if that's the case, then find a formula for the light. So there are two ways to do that. You can say that the intensity of the light is the intensity at the surface, so at the I0, at the depth is equal to 0, which we don't know what that is, just some number, random number, that we'll just call it I0 and leave it. You can plug that in depending on how bright the sun is, just leave it as some random number. And then there's two forms. You can write it as some base to the depth, some b, which we don't know what it is, that's the whole point, to d, which is the number of meters deep, or you can write it the other standard way. You can do exponents, which is I0 e to the rate of decrease d. Either one works, and it's real easy to convert back and forth, because in this case, this is the same thing as saying I0 e to the r to the d power, right? Because power is multiplied, that's rd. So in other words, our b here is just e to the rate. So if we know one, we can go back. If we do this form, we can go back and find what b is. It's just e to the r power. Here we figure out r, here we figure out b, and you can go back and forth. If we do it the other way, if we find b and we want r, then it's real easy to do too, because we just take the ln of both sides here. Ln of b is equal to r, because ln and e cancel. So either way we go, we can convert back and forth. They give you the answer in this form. They give you a b. So if you want to get their answer, you do it this way, but it's real easy to see if you check your answer. I like this way because r then actually tells you the rate that the water, that it gets darker. It gives you a percent. And so it kind of helps you visualize it when you figure out r. Here, this b doesn't really give you any feeling for what's going on, but e to the r, it does. So I'm going to do it this way, and then we can convert to that real easily. Okay, so they say then, in 15% for every 3 meters. That means at 3 meters, so I at 3 meters, it's 15% less than it was at the surface. So that means it's 0.85 times I0. If it's I0 at the surface minus 0.15, it's 0.8. And we always do the, with decimals, the math is on the decimals. 15%, of course, is 0.15. So it went down by 0.15. So at 3, it's 0.15 I0 e to the r times 3, because the depth is 3. Okay, now we solve for the rate. I0 cancels. So we have 0.85 equals e, and it's always nice to put the number first, e to the 3r. I don't know why I wrote an equal sign there. I don't really need that. Okay, we want to find r, so we take the natural log of both sides. That gets rid of the e. So the ln of 0.85 is equal to, take the natural log of this, I'll just write it all out, e to the 3r. Ln of e cancel, that's the whole point, they're inverse functions, so here we have 3r. So ln of 0.85 is equal to 3r, or the rate of decrease, r, is ln of 0.85 divided by 3. That you can put on your calculator, and I get 3 negative 0.054, I'm going to keep lots of decimal places, 17. So that is our, which is about 5.4%. So it decreases at about 5.4%, which ends up being at 3 meters, it's gone down about 15%. It's a little bit more than you'd think. You'd think, okay, in 3 meters it'd be 15 point something percent, because it's a smaller amount you're taking the percentage of as you go deeper. So it's kind of weird. If it's decreasing, the percent is bigger than you'd think. If it's increasing, the percent is smaller than you think, because it's a percentage of a bigger and bigger number. Anyway, and it's negative because it's decreasing. This is exponential decay. Exponential decay looks something like this. Starts off fast and eventually goes to 0, but takes a long time. Never perfectly gets to 0. It's asymptotic. But it starts off going down really quickly and goes to 0. Okay, so finally, our formula is I is equal to I0, just leave it like that, e to the negative 0.0541, 17d. Now, if we wanted to write that as the b to the d thing, like we say up here then, b is just e to the r. So if I go e to negative 0.05417, I get that that's I0 times the base, which is 0.94727 to the d. And that's because this number here is e to the negative 0.05417. You just plug that in your calculator. Again, because it looks like this. This is the base to the d power, because we multiply powers, we said before, and so you get that. And this, I think, is the answer that they would have in the back. Okay, that's the idea here. Again, this is exponential decay. Things drop off as negative exponents if it's an e, or if it's a b, it's less than 1. Because a number multiplied by itself less than 1 is always going to get smaller and smaller and smaller. Okay, that's how you do A. On B, they say what depth of the line intensity be decreased to 1% of its surface intensity. That means this is I then is equal to 0.01. So for B, I is 0.01 I0. And then we just plug it into either formula we want. That's equal to I0 e to the negative 0.05417 d. I0's cancel and you solve for d. And again, you have to use natural log to get that down, and I think you guys can figure that out. Okay, so that's the idea. Hopefully that makes sense, and I'll make another video showing one of the later problems.